Okay, we're all set, I think. So that was interesting about that little program you wrote to try out Michael's hypothesis last week.
Oh, yeah. I had almost forgotten about that.
Yeah. I hope he joins us today, and so maybe we can talk about that. So anything else TAOCP or Knuth related during the last week that you came across?
Well, I think you just reminded me, isn't today Knuth's birthday?
Oh, is that right?
Tomorrow.
Oh, wow.
Will be his
82nd, 83rd?
82nd, yeah, 83rd, I guess.
83rd.
Yeah. Tomorrow.
Wow, that's pretty amazing. Yeah. So I do know that, okay, Miguel is joining. Hi, Miguel.
Hello.
Yeah.
So Arthur just brought up the fact that it's Knuth's birthday tomorrow, January
It's whose birthday?
10th, I guess, right?
It's whose birthday?
Knuth's birthday.
Oh, really?
Yeah, 83rd birthday. So every year, you may have seen this on his homepage, he's been doing these Christmas lectures for the last, I don't know, at least 15 years, maybe even more, maybe 20 years now. So, you know, he would pick a topic. It's a lot of the topics have been on trees, but some other topics as well. And then he would talk at Stanford. I think generally around like the first or second week of December, and it had become this annual tradition. But last year, he did announce that there wouldn't be any Christmas tree lecture. Oh, maybe that's why it is generally on trees because the title is Christmas tree lecture. So, but I wasn't sure if that's because of the pandemic or, you know, because he's not feeling up to it anymore. But hopefully he's you know, feeling lively and he'll continue. And the rest of his engagements also continue. He talks quite a lot during the year, at least 3 or 4 public occasions from what I've noticed. Okay, we'll give Michael a couple of minutes. And we did have a new RSVP today. Not sure if that person will join. Yeah. So here's the agenda for today. We plan to finish off the merging section with the third variation on merge sort. It's called list merge sort. And then the next section is sorting by distribution, which has one main algorithm in it called Radix list sort. And it's actually a generalization or the more general version of the simpler distribution counting, I think that was called, the algorithm that we saw in our very first section on internal sorting. And so it's a little more elaborate. And then there's a nice discussion after the algorithm of other optimizations or variations that people have proposed on this. So that's kind of interesting. And then hopefully we can do some exercises. I won't have a chance to do the MMIX step through that I had planned for the list merge sort program. I wasn't able to get it ready and all cleaned up in time. So I'll probably record that some other time. And Hamilton maze. What is this? Oh, okay.
A puzzle from Knuth's last birthday. At least I think it was the last birthday. I was just poking around on his homepage news there.
So are you supposed to figure out the shortest path to blowing out all the candles?
Hamilton path, a path that visits every node, starting from one of the ones and going to the other one, visiting each candle once.
Okay. It would be nice if there were some animation and you could actually, in a sense, blow things out. Nice. All right, let's go ahead and start. So we are on chapter 5, and let's go back to section 524, sorting by merging. This is page 163 through 165. There's the algorithm, there's a little introduction, and then there's a table that, again, as usual, demonstrates the algorithm on some data. So we'll be reading till about 219. Hi, Michael.
Good afternoon. Sorry I'm a little late.
You're just in time to join the discussion. So we're going to just throw you in the deep end. All right, so who can bring Michael up to speed on list merge sort?
Well, I understand how it works with pointers, but I'm still puzzling out the small integer math that he's doing here with these indexes.
Yeah. So many moving parts, man. I have read this algorithm a few times already. Not now, like before today. I read it already several times. And again, same as Arthur. I understand what it's supposed to be doing, but it has so many moving parts.
Okay, let's just start with
saying like, okay, what was S then? Yeah, so LS is the what? So it took me a while to realize that what the first two things were, the first two numbers were. Like he got this two extra.
Miguel, what do you think it's supposed to do? Like, what is it? How is it doing things differently or the same as the first two merge sort algorithms, the straight and the natural?
So I'm going to say what I think I understand, but I'm pretty sure it's not completely it. So high level, you have one. Have a list of elements. You're going to add. So I still don't understand how you actually link them, but let's say you can somehow with integers. So each record has a link, has a field with a number that is pointed to the index, to the integer, not to the address, to the integer of the following element, to the next item in the list. So so the end result will be the bunch of records, when each record has a field with a number there, with integer number between a number there, the index of the following, so like a pointer to the following element. In order to get there, we're going to create two lists to be merged. And the way to create the two lists is first the conventions. If this index, this field, this pointer, integer pointer, it's 0, means that the list is over. Either it's a sublist or a whole list. If it's a 0, and you are traversing the list and you find a record with a 0 in the link field, the list is over. If it has a negative number, then it's the end of the known ordered sublist. So when you're doing sublists and you're traversing a sublist and you find a record with the negative link, that means that up to that point, the list that you were looking at, the sublist that you were looking at, was ordered. So in order to start the algorithm, you are going to initialize all these numbers by making all of them negatives. But not just that. So, so you don't know who is what is sorted. Therefore, they are all sorted. So you make one sublist per record that you want to sort. But the actual link is going to be jumping one, right? So the first element is going to be pointing to the third element, and the third element to the fifth, and the fifth to the seventh, and so on and so on, and the second to the fourth to the sixth. Like you're going to be jumping one, so you have two sublists essentially. You have two lists, not two sublists, two lists where all of the elements are, where each list is full of sublists of one element in order, right?
So do you remember the first two merge sort algorithms, the natural two-way merge sort and the straight two-way merge sort from last time?
Well, let's put it this way. I was just reading those two because I was trying to. I think today I got a little bit more intuition than last time about the natural sort. Like these things are being like tougher than the previous algorithms. I think today I got some intuition on the fact that you're doing a pass, moving things to the other half of to the other area, trying to keep when something is sorted, and then you start again, back and forth until some condition. I don't remember the condition that that everything is sorted. Why you ask, bud?
Because the basic idea in merge sort uses the concept of runs, right? So a run would be something that's just increasing. All the values are increasing, so that would be a run. And then the natural merge sort said, we're just going to use the naturally occurring runs in the array, and we'll just keep merging these runs, right? So every time we merge two runs, we end up with a bigger run. And eventually, the idea being that, the entire array would be just one run. And then in straight two-way merge sort, the idea was that instead of using the naturally occurring runs, we'll just artificially say that the runs that we're going to merge are going to be a fixed length, powers of 2. And if you start with the first power of 2 being 1, then obviously a single element is a run by itself. So you can always start from there. So you get runs of 1 length, and then length 2, then length 4, then length, up to whatever that power of 2 is that sort of divides the half of the array size. So what are we getting with list merge sort? That's sort of the question compared to those previous two algorithms.
What do you guys think? No, go ahead, Arthur, please.
Well, I was going to say we're not moving the elements, right? We're not physically moving these elements. We're leaving them in place and only messing with the links, which are small integers. So it should be more efficient if our records are large.
Okay. How are we dealing with the runs, though? Because now we don't have, this source area and then the output area. And so you can, easily traverse these runs in the array itself. Those are the values directly. So in list merge sort, how are the runs being handled?
I know they're being handled by the links. Also, the sign of the link in this case is indicating, are we at the end of a run? Or maybe the beginning of a run, or maybe it depends on your point of view. But that's not the full answer. I know that.
It's actually most of the answer.
So within a single linked list, we'll end up with runs. So we start out in the first L row of table 3. We've got these two lists, which he starts with the first indices in index 0 and index 17 for some reason. So the first list starts with element 1, and then it goes to 3 and 5, and so as Miguel said. But each of those links has the minus flag set, indicating that the run is only one element long at this point. And then by the time we get to the second row of L's, now our first list begins at element 2, and then index 2 says that the next element is element 1, and the element after that is element 6. But now we've got 2 elements in that run. That makes sense? Element 2 and element 1 are part of the same run. 087 and 503 are a run. And then we go to element 6, which is 170, and the element after that is 5, which is 908, and 170 and 908 are part of a run, and so on. So that part kind of makes sense to me. The mechanics of what we did to the numbers to get from row 1 to row 2, fuzzy.
Mm-hmm. Yeah, same with me. I was trying to. It's like too many. I read somewhere that humans are okay with keeping 3 things in the head at once. More than 3, it gets harder.
Yeah,
doesn't matter how smart you are. And we are trying to keep 4 things or 5 things, like five numbers changing at the same time. So it gets harder.
Yeah, it is harder, and I think what could help is if we just focus on one thing. And there, you have to choose, like, what is that one thing that you can focus on. But one of the things that I found interesting was that in the first 2 algorithms, there was a distinct source area and an output area. Like, these are 2, either separate arrays or 2 halves of a big array. And here, it's actually the lists that are sort of serving that purpose. So it's sort of like you're building that output area within these lists in some sense by just updating the links. And so initially you've got these 2 lists, and he wants to create, again, runs of a single element each. And so he's starting one of the lists at L0, the first artificial record, and then the other list is starting, or the head of that other list, the second list, is at that last artificial node. So those are the starting points. And then what he's saying is that within a list, you are at the end of a run when the link is negative. But you can still follow that link because it's the negative of the index of a valid entry. So there is a list that has half of the array. All the odd indexed entries are in one list, and all the even indexed entries are in the second list. And when they start out, both of these lists have runs of 1 element each because of the way the indexes, the links are initialized.
Mm-hmm.
But now, as time goes, as we go through each of the passes, we do the same thing like we did before in the first 2 algorithms. We go through one run and we compare it to the run from the other side in some sense. In this case, it'll be the other list. And then we merge them, based on whichever one is smaller or bigger. And you end up with a bigger run in one of the lists. At some point that terminates. And, then you just sort of alternate back and forth. So you keep doing that. And eventually these negative links, more and more of them turn positive because the runs get longer and longer. And if we reach a 0 for one of the lists, that means that list is exhausted. And then, the whole thing terminates when you've got a single list with the last link being 0. So that's how I understood it.
Yep, that sounds good to me. And I noticed that indeed the last line of table 3 is where number 17 becomes 0, indicating that that second list is now gone, right?
So,
everything has been in the first list.
Yeah.
Actually, what I wanted to do, but I never did, is to do the table, but also keeping track of P and Q, which I think is the whole.
We can try that. We can try that right now. So if you look at going from the first or the second row of the table to the third row of the table.
So P and Q starts with links. So are the links 1 and 2, right? So essentially they start literally with the first 2 elements of the original list, right? So you start comparing 5 of 3 and 0, 8, 7.
Yep.
And so that means that again P is the small one. So P is 1, right? P is 1. That's the thing that I guess I keep forgetting which number is P and which one is Q. So when we start, P is 1 and Q is 2, right? Because T is the end of the second list, right?
Mm-hmm.
And S is the beginning of the first list, possibly? No, cannot make no sense. What is that?
So S and T, I believe, start out at least as the beginning of the current run in each of the 2 lists. Right? We have these two.
Oh,
we have
I see.
two lists, and we're already partway into them. Right? At the beginning of a pass, we're at the very beginning, but that we're going to repeatedly merge 2 runs and then merge 2 runs, and so we're still at some point inside that list. And then P and Q are sort of pointers into like the actual elements that we're comparing within these runs. So P is in the first list, and Q is in the second list. LT.
So you're saying S and T are the beginning of each sublist? Is what you're saying?
No, there's 2 main lists. In fact, I shouldn't even say main list. It's just 2 lists. There's always just 2 lists. Mm-hmm. Every pass, there's always 2 lists. S is the list starting at 0. That's the head of the S list. And the last node, 17, is the head of the second list. That's always the case. In every pass, you always start with the S list on the left and the right, and the T list on the right. But within these lists, the runs are growing. So that's what's happening. Like each list starts out with just single element runs because every single link is negative. But now when you start out and you look at P and Q, that's telling you where you're going to start your comparison of the keys. So when P is 1 and Q is 2, that means we need to compare keys 1 and 2.
Right.
So which one will be
during the algorithm? In L4 and L5, we are updating S and T to the beginning of the run. I think that's what Miguel is saying, which I think is right. And when S and T finally gets to the end of the list, right, there should be somewhere in here where we're saying if Q is
in L5 and in L7 for Q and P, you keep increasing Q
until
you find that Q is negative, until you reach a negative link, right?
So at the beginning of every pass, S and T are always sort of the start of the list, right? But within each pass, S and T are being reused for different purposes. So when, for example, you exhaust one run from one list, then we just switch over to the second list because we can just merge everything over. So these S and T are playing, I guess, maybe calling the list S and T lists is not appropriate. It's sort of there's the two lists, and then within each list, when you're merging the runs, S and T are being reused for that.
So let me see if I get it. So we started with, we still are in P is one and Q is 2.
Yeah.
Right. So we get to step L3. So P is 087 and Q is 503.
Yep.
So P is actually less than Q. So we go to L4.
Oh, wait a
That
minute.
means, wait,
I see what S and T are doing.
what are they doing?
S and T are doing the same thing that K and L were doing in the previous algorithm, the straight two-way merge sort algorithm S.
So K was the index of the second area, right?
I had called out last time that L really wasn't being used in that algorithm. It was just a holding area. We were never reading L during the main algorithm. We were just, at the end of the step, we would swap K and L, and then we would be using L for a while, and then we would swap them back. It was just sort of a holding area. And the same thing is going on with T, right? We're doing everything with L sub S in step L4 and L5 are modifying LS, and in L6 and 7, we're also modifying LS. We're never modifying LT. The only thing we do with T is in L7,
L2, right?
and well, in L2 we initialize T.
So the only place we actually use LT is in L2.
And even there, T is, we're not really using T at that point. But what we're doing...
Right, T is always N+1, you're right. Yeah.
But in steps L5 and L7, which are duals of each other, we're taking that thing we had stashed in T and putting it in S.
Mm-hmm.
And then we're putting T forward somehow to be the best that we want. But again, so we're not really doing anything with S and T together. We're just using T as sort of a holding space for the S that we're not using at the moment.
So it's more like active and inactive output pointer.
Yeah.
Or in this case, they would be more like lists, you know, so which lists are we merging into?
Right. And before we had this D that was saying, the delta that was saying, are we appending this way or are we appending this way? Right, and they meet in the middle. And here with the linked list, we don't need that D anymore, because to get from one element to the next, you always do the same thing. You follow its next pointer. But still sort of conceptually, maybe this is the reason that he had the two lists starting at 0 and 17. Conceptually, we are still building them toward a middle. It's just that now they're not linear. You don't get from one element to the next by +1ing or -1ing. You get from one element to the next by following the next one. So the
partitioning is not sequential in that sense. You're sort of just creating this linked partition.
Yeah, or maybe you could say that it is sequential, but the notion of what it means to go to the next one in the sequence has changed. Yeah.
Okay, so I hope that adds to our understanding, but it is tricky, and it does take a few passes through that table to really figure it out. And definitely what Miguel mentioned about being able to keep track of P and Q, I found that almost necessary to really understand what was happening in the algorithm.
So my main concern, so I think we mostly got it, I guess. So I think if we really had to implement this on our own, we could. But after thinking more, right? Thinking way more than we have so far. It's not like we. So my main concern is how much is building the rest of what we're going to look at is builds on top of this?
Builds on top of these algorithms?
Of the intuition, not algorithms itself, but then, yeah, the intuitions of moving, the P's and Q's of the are the intuitions needed to understand these algorithms very needed for the following algorithms? If that's true, perhaps we should spend more time trying to get it right, or I will try to spend more time on my own trying to get it right in my head.
I have an answer to that, but I'd like to hear what other people say.
Do you mean the other algorithms we're going to look at specifically today, or like in the next month?
Whichever, I don't know.
You mean just TAOCP in general? Like?
Yeah, I mean, either in the next month or in fact today. It doesn't matter. Like, so I think I get it. I think I still don't got it. I'm there. Perhaps I just crossed the border, but I don't know where the addresses of the buildings are in a way. But just how more confident should we be for the rest of the algorithms based on what we got from this one? That's just wondering. Is the superficial understanding that we have enough for continuing, or we should try to make sure that we got it right in our heads?
My expectation is that you don't really need to know any more than we've done with this algorithm. I think the technique that's going to keep coming up, since we've seen it before, I predict this pattern will continue, that he's using these small integer indices where, a C programmer would use pointers. Like, we're going to keep seeing these tables of numbers that you have to sort of follow with your finger instead of.
Okay, let me. Right. Let me ask you differently. So, in the previous algorithms, my problem is I almost understood all of the previous ones mostly fine. I could keep track of all the indices somewhat nicely, right? But they jump from 2 to 4 numbers, and the number of indices is going to keep growing. Like, do we have to have a good index kung fu to keep track of the next of the following algorithms? And we need to make sure that we can handle 4, because next we're going to have to handle 6, and after that we have to handle 8 indices in the algorithm, and so we need to be super strong in our index kung fu.
Index fu. So it's hard to predict because you'd have to go through all of TAOCP to really say for sure. But I think the patterns that I'm seeing are, again, there's some algorithm that relies on some natural sort of way that you would approach it. So there's some general technique. Let's say for sorting, he's come up with these 4 or 5 different approaches, right? And there is a semi-naive, I shouldn't say completely naive, but semi-naive approach where you take that technique, whether it's sorting by exchanging or sorting by merging or sorting by insertion, and you just apply it straight to the data, right? And then we see some enhancements or tweaks that try to become more clever, but still sort of relying on that original storage space. Like you're just working in that storage space, or you're allocating some extra space, and then that takes us a little forward, and we get some better performance out of that. And then he seems to often introduce this linked variation, where you instead of trying to sort or to manipulate, rearrange the values in place, you just keep them as they are, and you work with links. And then this dual pointer approach or dual index approach, that's also come up a few times. So I kind of see these patterns reoccurring, and to the extent how complex they may end up being, I think it depends on the problem that is being solved. So my guess is that, yeah, they could become much more complex. In other data structures, once we get into trees, once we get into sort of multi-level, multi-linked structures, it could get complicated. So I would say understanding the patterns, just sort of becoming familiar with the way he sets up these things in terms of initializing these lists, and then using links in a certain way to help with the algorithm. I think that would probably reoccur, and you would see these patterns again and again. That's my guess right now.
All right. So bottom line, even if we move on today, at least I would try to make sure that I'm more comfortable with index food.
Yeah. I did implement this in C a few days ago, and I posted a link to that on the Meetup page. So what's interesting is that if you look at the algorithm, and he uses this notation, the absolute value sign, the bars around, like for example in L4 and L6, and maybe a couple of other places, L8 as well. When you're updating one of these lists, one of these links using that notation, you're supposed to retain the previous value's sign. And he mentions that this is something that you can do easily in Mix, because apparently it was using a sign and magnitude notation for the numbers internally, not 2's complement. So it's I guess it's easy to preserve the sign, but when you're working with integers in C or C++, that you can't do that because they're using 2's complement. So unless you have some way of sort of artificially keeping track of the sign, that's kind of tricky to do. So I implemented this using a double type for links that's cast to integers when we need them, because with doubles or floating point representations, you do have a separate sign bit, and so you're able to sort of retain that information if you wanted to. So that was kind of interesting that this technique is somewhat specific to Mix because of the sign and magnitude representation of numbers. And so a consequence of that is that, I think this is the first time we're seeing this, there is a different version of the algorithm, not of the program. The algorithm is slightly different in the supplement. So if we switch to the supplement now, page 89, there is a slightly different version. So it doesn't use the sign bit to indicate, whether you're at the end of a run or this is a continuation of the same run. I feel like the MMIX version that you're going to read is a little more complicated, but you may feel differently. Anyway, let's read that till about 258.
I think it's also worth pointing out that both of these techniques that he's used here, the putting the flag in the sign bit or putting it in the low order bit, you could really put it anywhere, right? I mean, these are you just need to find a bit somewhere, or it doesn't even have to be an identifiable bit. It just has to be a way of encoding Yeah, you could just say the index is like literally the index I if we're not at the end of a run, but if we're at the end of the run, it's 1,000 plus I, right? If the number is greater than 1,000, it means you're at the end of a run, and that would be totally fine. So he's kind of, I think, overemphasizing the exact bit twiddling that he's doing to find that extra representation.
Okay, so it sounded like Arthur had gotten the differences between the two versions. Do you care to explain?
I'm not sure there's more to say than what I said, but he's using the sign bit in the mixed version, and then in the MMIX version, he's using the low order bit of a field, and yeah, and I believe he's also using. Is he using pointers or is he using indexes times 8?
He's using, so the indexes are more like offsets, and then the offsets get added to some base address, so they end up being addresses. And because MMIX ignores the low bit, when it's actually retrieving anything from memory or storing to memory, he can, carry that information along when he needs to, or actually override it when he needs to. So I think that's sort of the idea in both of these algorithms is, as you said, Arthur, that you could have a separate, field or some way of representing this extra information about whether the run is continuing or whether the run has ended for a particular link. But he's just decided to encode this in the link itself for efficiency, and also I think that it makes the representation a little nicer because you have this compact representation. It's either a negative number, positive number, but the index is still valid either way. So it's kind of interesting, yeah. I did write a version of the MMIX variant as well. That was a little trickier with C, because with pointers, you don't get that automatic, aligned resolution of the address. So you have to do that explicitly. But it was interesting to try that out.
I think it would also be interesting for someone who was, going through doing MMIX-centric exercises, which totally we have not been doing, but make a version of program L where instead of using the tag bit the way he's doing, at the bottom of page 90 in the MMIX supplement, he says, for convenience, we assume the records are 1 octa long and they consist of these 2 tetras, where the first tetra is the index field, sort of the next pointer, except it's not a pointer, it's an index. And the key is in the high tetra. But then that first tetra, the link tetra, has this additional tag bit, right? So it would be interesting to make a version of program L where instead of using 1 bit out of that tetra, you just said in that tetra, the low wide is the index and the high wide is are we at the end of a run. So you don't have to do any bit twiddling to pull out that bit or to test it. You just have 2 byte quantities next to each other. Of course, this limits you to only being able to handle 65,000 elements in your list, right? Because your indexes can only go up that high. Whereas his is good up to 2 billion, I guess. But, given that this is, I think, also hard-coded to be is this hard-coded to be 16 elements, or?
What is hard-coded to be 16 elements?
In table 3, we had 16 elements in our list. Is program L...
No, none of the programs are all the programs are general, but it's just that he chooses to use that 16 element array as an example. But they'll work for anything.
Okay.
All right, cool. We have a couple of minutes. Let's just quickly go over the program, just continuing in the supplement. So this is pages 90 through 92, and there's a little bit of analysis, sort of a summary of the performance at the end, and then we'll take a break. Okay, let's take a 10-minute break, and when we come back, we can just recap, list, merge, sort, and then continue on to the next section. See you at 3:17. Okay, we're back.
Alrighty.
And I found this interesting note in the GNU sort source code. That program is part of the GNU core utils package, and in their to-do file, they have this entry about trying out list merge sort and their experience with that.
Interesting. Well, they're probably also really old. When do you think was the last time this was updated?
Back.
Or when did this date from? And the answer is probably, well, I guess it couldn't be older than 2002, theoretically.
Yeah, I think, yeah, when would this be from? I remember looking this up. There was some mailing list reference to this note. And I think it was from the early 2000s. So,
Actually, GitHub's blame is surprisingly quick. And indeed, it's from like 2003. But maybe at some point I'll get around to it. I've got stuff like that.
yeah. So that's kind of weird, right? Like they had such bad performance. Um, so I don't know. It's definitely worth wondering about, like, why would that happen? Anyway, so let's go on to where are we? Sorting by distribution. So this is the next section in TAOCP. Page is 168 through 171, and there's a table, as usual, table 1, that is helpful. Okay, who wants to take a shot?
Take a shot at what?
At explaining the approach and maybe table one, what's going on in table one.
Yeah, so the algorithm works by sorting from the least significant to the most significant part of the key. They use an example of digits, but later on, he says that if you have large keys, like a 40-bit key, you could break it down into 4 groups, 4 digits of 10 bits each. So that's 1024. So you'd have 1024 piles. You start by putting the things, reading the things from your file and putting them in the piles indexed by the 10-bit key. So you start with the least significant key and move on up. You put them together after you're done, and you put them on up. It comes together with the table. In the table one, you are working with just the digits. So in the first pass, what you're doing is you're sorting by the least significant digit. What you do first is you count the number in each digit. So the counts of the digits, that first one, that upper leftmost one, means that there's something somewhere that ends in a 0, and there's only one of them. And the second one means that there's something somewhere that ends in a 1, and there's only one of them. And then there's 2 that end in a 2. And you're just doing this so that you get the size of these piles. When he explained earlier by sorting cards first by the rank and making piles of everything with the same rank, but ignoring the rest of it, because the way he wanted to sort the cards was he wanted to sort them so that clubs, in the order that he said, clubs was less than diamonds, was less than hearts, was less than spades. So now after you've counted up the number of digits, now you add them together and you say we're going to need 1 space for the things that end in 0. The things that end in 1 are going to start at position 2. 2 plus 2 is 4. 4 plus 3 is 7. 7 plus 1 is 8. So that's how you get the 1, 2, 4, 7, 8. That just tells you where, and that just tells you where each of the groups go. And then you start from left to right, and you move these input into the auxiliary area. So the first one is 503. That's going to go where in the third pile. So if you look in the third column of the subtables there, that third column says 4, so the 503 goes to position 4. Then you take the 087. The 087 ends in a 7, so you go in the 7th column of the table, and you see that goes in offset 10. And by the way, also, as you move these things, you're going to have to increment that storage allocation. So when you move the 503 into position 4, you would increment the 4 to be a 5. So the next element that you found that ended at a 3 will now go into position 5. And you repeat that process for the middle digit and for the top digit. That's all it is.
Okay. Could you explain what he said about, at first people thought that, you would need m plus n times n space for the card, analogy applied to these arrays. But then using the counts, it turns out that you only need an extra n amount of space.
Okay, so when you think about breaking things up into piles, all the digits might end in 0, or they all might end in the same thing. So the maximum size your pile would be n. And if you we're making the piles separate instead of contiguous, you would need n piles, of which the maximum size could be n. That's a naive way of doing it, but that needs a lot more memory. And then you wouldn't, so he gets around that by saying, okay, if we count the number of elements that end in each digit, or that will be allocated by each digit, we're only going to end up with n, and we need a little bit of extra memory for the to keep these tables. These smaller
counts.
tables have 10 elements each, and then the input area could have 1,000.
Did you find it surprising that it took a while for somebody to discover this?
I think programmers from the 50s were doing this. I just think it took a little while for somebody to say, hey, this is exactly what's going on.
Okay.
It's not that hard. I know I ran into it early on in my career, but that would still be later than.
Okay,
Yeah,
so what you're saying is that you feel like it was sort of like common knowledge, but nobody had really published it or formalized it until 1954.
Yeah.
Okay.
Yes, I really think so.
Okay, cool. Any other questions about Table 1 or the approach? Comments?
I put one comment in the chat that might not have been obvious to the casual reader. Talking about this inventory simplified tabulating machine method of doing a sort of multiply add, right? You've got a whole bunch of cards that have two numbers on them, and you want to compute the sum of their products. And then he goes immediately into this like complicated rigmarole about, how you sort them and so on. But he doesn't say really why you're doing this. And reading between the lines, the why is that if you just did the obvious thing of, well, for each card, multiply the numbers together, that would be hundreds of multiplications, right? One per card. And multiply was one of these slower operations. I mean, still is, one of these slower operations that you can do. Whereas if we can just do it in terms of, I guess, additions and comparisons and shuffling cards around, in those days, that would actually have been faster than doing the multiplications. These days, I don't know so much, right? Memory is slow these days. But here, shuffling around cards physically is maybe going to be faster than asking the computer to multiply a whole bunch of numbers.
Okay, great. So let's now look at the algorithm, which is a little different from the introduction. This is a linked version of the algorithm. And in fact, the introduction starts around the bottom of page 170, where it says an alert modern reader will note. So you may have already read that paragraph, but if you haven't, that's where it starts. And then there's actually two algorithms. There's the main sorting algorithm, and then there's algorithm H that follows. And then there is also a figure 33 on page 173. So we'll just discuss all of these together in about 7 minutes. Yeah, it's nice we don't have to look at mix. That would be quite something, self-modifying code. Um, all right, so did this pretty much match up with the table one that we saw, like the approach here? Is it almost one-to-one, or were there some tricky parts to the list version?
Well, because you're using the list, you don't have to go through that phase of counting, which seems kind of inefficient. You're just building a list instead of counting.
Okay. Anything else you feel like worth pointing out? In figure 33, does figure 33 match up with table one, pretty one-to-one, or was there any confusion there?
Figure 32.
Figure 33, no, 32 is the flow chart, but 33 is,
Got it.
the,
Oh, yeah, okay.
that sort of corresponds to table one.
Yeah, if you read through the piles from the top down, left to right, so piles left to right, and you up down it, you come up with the same ordering of elements in each step of the algorithm.
I felt figure 33 was a little magical. Just if you just look at figure 33 and you realize at the end things are sorted, it's very interesting. Whereas table one seemed a little more straightforward and in terms of just understanding, but figure 33 just seemed like wow.
It's kind of hard because you got to realize that the 087, 061, 170 haven't been moved. You're following the pointers. It looks like they've been moved into piles. He's just showing the individual lists that we've built.
Yeah, that's why I felt like it
actually moved. But if you tried to draw it on the input, I imagine it would look like arrows all over the place, a little bit like spaghetti.
I find figure 33 very natural and easy to look at. Although I agree it's not obvious like how the magic happens unless you focus on a specific pair, like following either 512 and 612 are interesting because they end up in the same bucket for the first two passes and only split up at the end, or 503 and 509. Which are in the second, which are in the zero bucket in phase two, and it's not until, or no, never mind. Yes, I guess the thing is that 503 and 509 are in the correct order already in phase two, and that order is not lost in phase three, which is important. That the sorting algorithm that we're doing in each step. Well, it's not really a sorting algorithm, but yeah, it's a sorting algorithm. We're sorting right all the zeros to the left and all the nines to the right. But whatever algorithm we use to do that has to be stable. And it turns out it's a very simple algorithm. But
okay. Any other comments or questions? Well, let's have a quick look at the program in the supplement, pages 93 to 94. Okay, any comments on the program?
The version of MMIX Supplement that I have must be an entirely different edition because I can find the Radix list sort and it's in MMIX, but it's on page 149. But the page
wow.
numbers aren't numbered. So
do you,
actually, take away, there's about 15 pages in front, so it's actually probably about page 120 or so.
are you looking at an online version?
Pardon?
Are you looking at an online version, electronic version?
It is an electronic version, yes.
Yeah, so my guess is whatever that was generated from, it wasn't the, the hard copy.
There are about 20 pages of Roman numeral preface stuff. I have the hard copy, paperback edition, and there's about 21 pages of preface.
Yeah, there's a lot of stuff, but it's hard to find. I mean, I have to, but then the good thing is I can search by Control F.
Yeah, right.
I had hard copies of all these things, but I lost them in a flood.
Okay.
Oh no.
I also have Riley. I could get it there, but that's kind of a page at a time. You can't download it from Riley, I don't think.
Yeah, I don't think you can. Yeah.
That doesn't have the page numbers either.
Okay, so let's move on to the analysis. This is back in TAOCP itself, and there's like a couple of pages on proposed enhancements and things that people have found out on variations. So, about 7 minutes on that. All right. Any comments on the analysis or the enhancements or variations?
Well, I thought it was noteworthy that he mentions again this idea of a hybrid sorting algorithm that starts with most significant digit first radix sort, and then when you get down to like a mostly sorted array, you switch over to insertion sort or something like that.
Yeah, that's definitely very interesting. The most significant digits of the least significant digit portion. And also the very last sentence on page 177. That might be interesting to investigate. It seems relatively recent, and it sounds like, like when he says well-tuned, it may be appropriate for some applications. Anything else? Do we have time for a couple of exercises? Can people stay on?
Well, I can stick around for a little bit.
Okay, cool. By the way, there is a nice table on page 382 of TAOCP. It summarizes the performance of the different sorting algorithms we've seen. And there's an MMIX version of that same table as well, page 96 of the supplement. You can look at that whenever you get the chance. So exercises, if any, seem compelling, we can have a look at those. But I did find number 4 and number 8 kind of interesting. So this is on page 177.
Well, for exercise 4, it's basically saying in algorithm R, we're using these piles, which are queues, and we hook them together. I guess head to tail. And so what if we get rid of the tails? Actually, I guess I am a little bit confused what this means. How do we hook them together at all if all we've got is heads? We wouldn't end up with a snake composed of segments. We'd end up with an octopus if we linked all their heads together. That's not something we can do. But assuming we're still saying we're going to link them head to tail, it's just that when we insert things now, we're, instead of pushing them on the end of a queue, we're pushing them on the head of a stack. That means basically their order is reversing every time we do this. And so when we link them together, we want to keep in mind that we've just reversed the order of everything. and so link them together. You still had the tail, but in the reverse order, like
So,
pile 9 to pile 7 and so on.
Arthur, if we go back to figure 33, how would that last row look like in figure 33 if we were using stacks?
The last row.
On page 173.
Yeah, you mean the by row you mean sort of whole phase, right?
Yeah, yeah. The last pass,
well,
the third pass.
You wouldn't have the bottoms, you'd only have the tops.
Mm-hmm.
And then in order to link these things together, I think you would have to start at top of 0 and follow the pointers. Wait a minute. Actually, no. The question is, how do you get to 0, 6, 1 if you haven't got a pointer to it anymore? Right. If we've only got the tops, we've got a pointer to 0, 8, 7.
He says the arrows in figure 33 would go downward instead of upward. And then the bottom, entry would no longer be needed.
Right. So then our algorithm for linking heads to tails would have to traverse the whole segment, right? Start at tops of 0 and follow the links until you get to one with a null link. That would be 0, 6, 1. So you say, okay, that's the tail of this list. I'm going to link that up with 170. Except you wouldn't actually do that, right? You would actually start at the other end, at top 9, and you would say 908 gets linked to 897, gets linked to 765, which is already linked to 703, and its next pointer is null, so we link it to 677, which is already linked to 653, and so on. And every time you do this, you're reversing the order of the list. Right? So now we've got a reverse sorted list here. And that will automatically undo itself on the next pass. The only issue is if we have an odd number of passes, which is what we have in this case, right? We have 3 passes, and we end up with a backwards list. But reversing the order of a list is something we can do trivially in linear time.
So does this lead to a simpler or a faster algorithm? I guess these are 2 different questions.
Well, it takes less space. Not that we really care about saving those 10 words of, it saves you the 10 words of bottom.
Mm-hmm.
For an even number of passes, it's probably a little bit faster but for an odd number, you got to reverse the list, and that adds a.
Is it simpler?
Well,
is it simpler? No.
No. Yeah. Yeah. Okay.
I don't think it's going to be faster either because with the Q version, it's very quick to link up bottom sub I and top sub I plus 1.
Yeah, but
right?
you gotta maintain those bottom segments, and you don't have to do that in this one.
By maintain, you mean the clear part of it, or you have to clear out the bottom pointers again?
Yeah, that's gone on this. It's exactly the same. It's exactly the same as the other one, except there's no clearing of the bottom pointers, and there's one less pointer per stack. But in order to find that bottom pointer again, you have to traverse the entire list. Right? You're saving 10 clear operations, but you're paying n pointer following operations, because with only top sub. No, wait a minute. No, I don't see that, because you no longer have that bottom that needs to be maintained. It's not just clearing, it's when you put the first element in, you've got to update the pointer on that bottom instead of just updating a root pointer. You have one less node in each list.
Suppose you wanted to link the bottom of stack 5 with the top of stack 6. Or, sorry, vice versa. Let's link the bottom of stack 6 with the top of stack 5. Right? That's what we need to do at some point. Link the bottom of 6 with the top of 5. How do you get the bottom of 6?
I'm not really sure whether it follows, but yeah, I see what you're saying.
You can do it because all the arrows were reversed, but you have to follow all of those arrows to get there. You no longer have a bottom pointer pointing directly at the element you want to modify.
Why do you say the arrows are reversed? The arrows are the same. It's just that we only have the pointer to the last one, the last node.
Well, looking at figure 33, you can say either we'll just keep the bottom pointers and throw away the top pointers and leave the arrows the way they're going. But yeah, the way Knuth says it is keep the top pointers and reverse all the arrows and throw away the bottom pointers.
Yeah.
But somehow we need a way to get from the pointer that we kept.
Okay, why do we need to link? Why do we even need to link the tops to the bottoms in an intermediate step? That I don't understand. You're just going to follow what you're going to do on the second pass. You're going to look for the second digit, and you have 10 lists to do it through. Why do you need to? You just go through one list. You're building a new set of lists. You go through the 10 lists one at a time. You don't need to link them together. That's the way I'm thinking of it. So I don't see. You're thinking at the end of the pass, I've got these 10 lists, and I'm going to I'm going to link them. I'm going to have to link them together. But I don't have to. I have an array of 10 lists. I just go through each list once, and now I'm looking for the next digit up.
But you're also building an array of 10 lists.
Yeah. Yep.
So you're saying keep 2 arrays of 10 lists, which is what we have here. Right?
Yep. Yep.
But if you want to see it,
it's the same thing either way.
If you want to avoid keeping an input buffer and an output buffer, what you can do.
No, wait! It's a list. You're not keeping an input buffer. You're not keeping an input buffer and an output buffer except for the lists. I
say you are. If you want to avoid doing it.
No. The link pointers are up. The link pointers
so that you end up with just one list. You only
have 10 pointers
to keep track when you're going through memory. You're going through this single list from beginning to end. And
you're not getting me. 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 The extra memory that you need is an array of 10 pointers. Those are your heads. Remember, the links are part of your records, and they're in place, but you're updating them. So if you have 1 million records, you have 1 million links. You're not going to copy those links. You're going to be changing them. Now you need an auxiliary list of 10 pointers, because I think you do anyway, because in the end, when you do the second pass, I guess you're going to, unless there's a clever way of reusing the same memory for the second set of piles, you're just going to go through. You have the ones that end in 0 in the first list. You go through them based on the second list, and you're building a second set of lists, and you go through each one 0 through 9, and you end up with a second set of lists that are now sorted on the last 2 digits. You see what I'm saying? You don't have to go to the end of the list and link it to the next list. You'll do that anyway when you're sorting the next digit. And there's no need to keep a separate output buffer, except for the head pointers. So you have 10. You do have a little bit of extra memory. You have 10 pointers, and I guess the way I'm seeing it is there's an auxiliary list of 10 pointers. So you do the first pass on head pointer set 1, and then the second pass on head pointer set 2, and then back to 1 and back to 2. I think that'll work. Silence. Okay, can you guys hear me?
Yeah, we hear you.
Yeah.
Okay, let's look at exercise 8 if we still have a bit of time. So we were looking at just non-negative keys for radix sorting. What if we had negative values in either 2's complement or 1's complement? Would we need to change some things?
What comes to mind immediately for me is that the digit is just another, the sign is just another digit.
So let's say that we were doing
oh no, that's not
least
right.
significant digit. How?
No, that's not right. That's not right. It's probably the right idea, but it's -1 is bigger than -2. So if you sorted -1 and -2 on the digit first, you would get, yeah, it's probably the right idea though.
Okay, so you're saying how?
Well, basically, that most significant bit has the opposite semantics now. If these were unsigned numbers, then having a 1 in the most significant bit would mean you're really large and you sort after the zeros. But if you're doing 2's complement, having a 1 in the most significant bit means you're small. And so I'll try my camera again here. If we have an array of bit strings and we treat them as unsigned integers, they're in order. If we treat them as signed integers, what we actually need to do is swap the halves, right? These ones with the 1-bit set are actually small. They need to go at the bottom. And so we can do that by just the very last time we stack the piles, we stack them in the opposite order. And that should work.
So what if you did, instead of 10 piles, what if you did 20 piles from -9 to 9? Or, yeah, -9 to, that would be only 19.
Well, we're doing this with bits to begin with because that's the only way it makes sense. But yeah, I guess you could do that, do a decimal version of it where you have -9 to 9 and just the negative piles are always going to be empty except on the last pass, right?
The last pass is no different. You're going to have the negative sign. Yeah.
But during all of the other passes, you don't have any negative digits, right? The least significant digit of...
No.
Right.
On the pass, you have to look at the sign of the number, and on the first pass, you look at the sign of the number and the very least significant digit. And that'll be a number between -9 and 9.
Mm.
And so you build 19 piles that way. The negative number it's going to be negative all the time. Will that work?
Yes, yeah, you have to combine the overall sign of the number with the digit every single time. You're right.
I think that'll work. That seems to be the easiest way to do it.
Yeah, I think that'll work. You're just sort of extending the radix in some sense. You're doubling the radix, right?
Well, that's yeah. Well, you're doubling the number of piles, so it's going to take a little bit more memory.
Mm-hmm. Okay. So as I mentioned in the Meetup page, this will be, for now at least, the last Meetup on sorting.
What is Knuth's answer on that one? Which number is it?
That's number 8. I haven't looked at the answer. No.
No, I'm just curious. Because it came to me right away, and usually these are harder than that.
Well, if you're asking about the rating, it's a 20 rating. So it's not, super hard.
Yeah, but most of the problems that have a 20 rating, I do not immediately think I know how to do this.
Okay.
But that one, almost before I finished reading it, I knew how to do it. Or I said it immediately came to mind. Just just consider negative numbers to have negative digits and use that number. It seems to work.
Yeah.
I'm just curious what his answer is.
So you're getting
I'm kind of thinking that I'm wrong, and everybody's agreeing with me.
You're getting the hang of Knuth.
Knuth's answer is on the last step, flip the files, and just do it, with Radix too. But I believe your answer is a way to do it with radixes other than 2. Maybe the most convenient way to do it with radixes other than 2. But with radix,
so he's thinking binary, and I'm thinking with digits.
Yeah, he did mention the binary representation in the question, to be fair.
Yeah, but that binary can be translated into digits.
Oh yeah, sure. But I think that was sort of the intent.
All right. Fair enough.
Yeah. So we will continue back in volume 1, and we'll start off with the sections on trees. There's a couple of sections for linked lists that we had skipped, and we'll probably come back to them later because they have, one of them at least needs a little bit more MMIX features. So we can cover those later. And the other one, I don't think we need it right away. So we'll start with trees, and then there's a few sections that are sort of basic and fundamental, and then there's some more advanced stuff, and we'll probably finish off the linked list section before we do that.
Okay. When I read these books, when I had them before my flood, I remember the next section continues with sorting, and it gets into some really interesting stuff of basically the problem is you have more records to sort than will fit in memory. And the way that I read it way back then was that the extra records that don't fit into memory go on tape, and you could read the tape sequentially. How do you sort it? You can have, how can you sort it if you have 5 tape drives? That kind of problem. And they're very interesting. I remember that part. I don't remember any of the algorithms, but I remember the type of problem. I think actually, now that I'm thinking of it, those types of sorting may actually be relevant for big data today. We don't use tape drives today, but we have data that's separated across very many nodes. It's not it's very many hard disks, like very many file systems.
Yeah, so you're right. There's a huge part of volume 3 that's devoted to external sorting, and he still has the tape algorithms in there, plus disks and some newer stuff. And you're absolutely right. Like when you really think about sorting, where it starts to make a difference is external sorting.
Right.
These internal sorting algorithms, I think they're really good and fundamental because everything else is sort of built on these approaches. But sorting in memory is really not that critical when you really think about it. If you do just okay picking an algorithm for in-memory sorting, that's fine. And that's why you don't really have a lot of choices in terms of in-memory sorting. When you look at standard libraries, they'll just generally just go with one, and that's it. And sometimes you'll have some specialized libraries that can offer other algorithms, but most people don't spend a lot of time figuring out like which internal sorting method should we pick. But for external sorting, I think it makes a huge difference. And like think about databases and the techniques that they use, and I think you're absolutely right. Like in the age of big data, this could make a big difference whether you find an efficient radix sort, based on the nature of your data, or you find some other variation of merge sort. So that is
Right.
definitely interesting. We will definitely come back to those sections. My guess is when we come back to volume 3, we'll have a choice of either starting on external sorting right away or starting with searching. So they're kind of independent in some sense.
Right.
But
Well,
yeah.
you're the leader. I mean, I wasn't meaning to suggest that I wanted to continue on with sorting. I just remember reading the first section through on my first read through of this like 15 years ago, and this part that we covered. This is all stuff that I got more or less in my master's program in my algorithms class. But when I got to the next section, that was all totally new stuff, and I got the feeling that all of the answers weren't even known.
Yep. Okay, great. Thanks a lot for attending. Hope to see you folks next week. Bye.
See ya.